Good day, everyone. In this lecture, we will be applying what we have learned so far to this popular model, the so-called Gaussian linear model. Indeed, many problems can be formulated as the estimation of the parameters of this model. This model requires that the relation between the mean of the data and the parameters that we want to estimate is linear. And this is actually an assumption that holds true in many practical situations. This is, for instance, the case in curve fitting, right? In line fitting, regression, things like that. But even if this relation is not linear, one can still use the Gaussian linear model as an approximation to come up with a simple estimator, right? This is of interest, for example, if in the task we need to accomplish, we don't really need a very good estimator. Perhaps it is enough to have an okay estimator. Or maybe we are given a complicated nonlinear model, and before we start spending many hours on trying to derive a very sophisticated estimator, we can just use the Gaussian linear model as an approximation and come up with a simple estimator that tells us if there is light at the end of the tunnel, right? And one of the benefits of adopting this model is that the MVU estimator exists, and we will be deriving it later today. In the Gaussian linear model, the data can be expressed as a linear function of theta plus some noise, right? We will be using throughout the letter capital M to denote the length of the parameter vector, that is the number of parameters that we want to estimate, and we will continue to use N to represent the number of samples. The matrix featuring in this first term is, of course, of size n by m, right? And it is referred to as in multiple ways. Can be observation matrix or measurement matrix, sampling matrix. Depends on the context. And the noise is assumed to be Gaussian with zero mean and covariance matrix sigma, which is obviously of size n by m. Okay, so here this first term is deterministic. This matrix is deterministic, but this W is random, right? Which implies that X is also random. Or even more specifically, since this is has this distribution, it follows from probability theory that X needs to adhere to a Gaussian distribution with this mean, right? This first term is the mean, and this covariance. Okay. We will assume that this H and this sigma is they are both known, okay, and our problem will be to estimate the parameter vector given the data X. To help us appreciate the relevance of the Gaussian linear model, let us consider some examples. The first one is our favorite toy example, estimation of BC level. Remember that under this model, the data is a constant that we want to estimate plus some noise, right? And remember that this can be expressed in vector form in this way, where this is the vector of all ones. Okay. Just by inspection, we see that this expression is a special case of this one. If we define theta to be the vector with a single entry, this entry being the parameter A, and H a matrix with a single column, this column being the vector of all ones. I would like to take this opportunity to introduce a terminology that is very common in signal processing. We say that the noise is white when its covariance matrix is a scaled identity, and we say that it is colored otherwise. This terminology comes from physics, more specifically from light physics. The idea is that if the entries of each entry of W represents the component of light at a given wavelength, then the covariance will be approximately a scale identity for white light and different from it otherwise. So the idea is that, or this means that the components of the wavelength components of white light have more or less the same frequency and are uncorrelated with each other, right? Another example is that of amplitude estimation. So suppose that the data is a scaled version of a known signal, but we don't know this scaling factor and we want to estimate it, right? This signal can be, for example, a sinusoid or an exponential or a pseudo-random sequence, something like that. So one can think of, for example, in an application where one device transmits a pulse or a signal, and then another device receives that signal and perhaps wants to estimate the amplitude to determine how far the transmitter is, or whether, I mean, perhaps there's some material in between transmitter and receiver, so perhaps it wants to determine the absorption or something like that, right? Again, this can be expressed in vector form, in this case by defining this vector S, right? And it can be seen that this is just, again, a special case of this expression here. If we define theta in this way and H to be a matrix, again with a single column, but in this case this column is this vector, okay? Another example is line fitting. So suppose that we are given a set of points, right, of pairs of values of the variable, in this case z and x, and we would like to determine or find a line so that these points lie close to it, right? So we need to find the slope and the ordinate of the line, right? So to formalize this wish, one can postulate that the values of x are this affine function of z plus some noise, right? So this noise accounts for this deviation here from the line to the points. This can be expressed in vector form, right? Just by defining this vector z, okay? And again, one can see that this is just a special case of this expression here, if one defines h and theta in this way, right? So note that now theta contains two entries because we want to estimate these two parameters, okay? So the next step is to derive the MVU estimator, but before that, let us look at one very important notion in estimation theory, which applies in general, but it is easy to understand in the Gaussian linear model. So to develop some intuition, let us look at some example. And before, suppose that our samples are the sum of two parameters plus noise, and just assume, for example, that our noise is Gaussian and white, right? Remember that this says that the covariance matrix of the vector and W is a scaled identity, right? Just two different ways of writing the same thing. And the problem is given the samples to estimate A and B. Okay, so to see if this is possible, let us look at the distribution just by using standard probability theory facts. We can conclude that the distribution of X is Gaussian with this mean and variance sigma squared, right? So what we observe here is that this distribution depends on A and B only through the sum of A and B. That is, for whenever for two different combinations of the values of A and B with the same sum, the distribution is the same, right? So, for example, the distribution is the same when A is 1 and B equals 3, or when A is 3 and B equals 1, right? So this is essentially saying that there's no statistical way of obtaining the value of each of these parameters separately, right? So there's no way in the world we can come up with a reasonable estimator for A standalone or for B, even if we are given an infinite number of samples, right? So in this case, we say that these parameters are not identifiable, right? Or more formally, this is in general for any estimation problem. We say that two parameters are not identifiable if for two different values the data has the same distribution. Okay. Again, this is not specific to the Gaussian linear model, and it is something that we need to check every time we want to solve an estimation problem, right? Because if the parameters we are trying to estimate are not identifiable, we are just wasting our time. All right. So let's see how this condition translates when under the specific case of the Gaussian linear model. So under this model, remember that this is the distribution of the data, and we therefore say that the parameters are not identifiable if there exist two different thetas for which the distribution is the same. So in this case, this obviously means that h theta 1 equals h theta 2, right? So an equivalent condition is obviously that h times theta 1 minus theta 2, right? I'm just moving this term to the left-hand side must be equal to 0. Okay, and this vector theta 1 minus theta 2 will be different from 0, right? Because theta 1 and theta 2 are different. So by just linear algebra facts, this means this happens if and only if this matrix H doesn't have a full column rank, right? Remember that this matrix is n by m. Okay, so if this is rank deficient, then the parameters are not identifiable, right? So therefore, whenever we solve we are trying to solve a problem with the Gaussian linear model, we need that the rank of H equals the number of columns, right? So the columns of H need to be linearly independent, right? And this is an assumption that entails no loss of generality, right? And the reason is that whenever there are linearly dependent columns in H, we can just remove some of the dependent columns, and the model will essentially be the same, right? And so in this case, for instance, what we just can hope for is to estimate the sum of A and B. So this would be just replacing this with an equivalent with a single parameter. Okay. Okay, so now we are ready to derive the MVU estimator, and remember that the method that we use in this course to do so is the application of the Cramer-Rao lower bound theorem. The assumptions are, of course, that the matrix H is full column ranked, right? So the parameters are identifiable, and we will start by assuming that the noise is white. We will perform the extension to colored noise later. To apply the theorem, the first step is to find the likelihood function, right? This just follows by the PDF of the multivariate Gaussian distribution, right? So remember that this is the distribution of the data in the Gaussian linear model, right? So the Cramer-Rao lower bound theorem requires that regularity condition holds, right? The expectation of the gradient of the log likelihood function must be 0. So let's check if this condition holds. The log likelihood function is obtained just by taking logs in the likelihood function, right? This is a straightforward computation, and the gradient can be obtained just by applying the chain rule here. Okay, so again, if you are not comfortable with the chain rule, there's material in the shared folder where these slides can be found, and that material explains the Jacobians, gradients, Hessians, the chain rule, and so on. So after simplification, we obtain this expression. And the expectation of this equals, of course, the expectation of this other term, and applying the linearity of the expectation operator, this expectation comes inside these brackets, right? And using the fact that this expectation equals h theta, right, we see that both these terms cancel and we obtain 0. Therefore, the regularity condition of the Kramer-Rao lower bound theorem holds, and therefore it applies to this case. The Kramer-Rao lower bound is provided in terms of the Fischer information matrix. So let us compute this matrix. And to that end, we need to obtain the Hessian of the log likelihood function, right? And by the facts in the that you can find in the document on derivatives that I mentioned earlier, the Hessian is just the Jacobian of the gradient, right? And the gradient can be obtained, or we obtained it in the previous slide, so it can be substituted here, right? And just by obtaining the Jacobian of this expression, we find the Hessian, okay? The Fischer information matrix is minus the expectation of this Hessian, right? So we can just substitute this here, and since this is deterministic, right, it equals its own expectation, right? And therefore this is the Fischer information matrix. So the Kramer-Rao lower bound theorem then states that the covariance of any unbiased estimator is lower bounded by the inverse of the Fischer information matrix, right? And the Fischer, the inverse of the Fischer information matrix is obviously sigma squared times H transpose H inverse in this case, right? So as always, we need to check if the matrices we are inverting are actually invertible, right? If they are non-singular. So here it is easy to see that this product H transpose H is m by m, right? Because H is n by m, okay? And the rank of this product is also by linear algebra facts equal to the rank of H, right? And we said that our assumption that the rank of H equals m. Therefore, H transpose H is an m by m matrix with rank m, and therefore it is a full rank. It is invertible, right? So everything is okay. So note just what happens when the parameters are not identifiable. Suppose that the parameters were not identifiable, right? So in that case, this rank is less than m, right? And this matrix is not invertible, right? So we can see that the Fischer information matrix would not be invertible, right? So whenever you encounter yourselves in a situation where the Fischer information matrix is not invertible, right? So you know that you may have some identifiability problem, okay? As a sanity check to to see that or to corroborate that this is actually correct, you may derive the Kramer-Rao lower bound using this expression for the DC level estimation example, and see that you get the same result as we obtained in the previous lecture, where we also derived the Kramer-Rao lower bound for DC level estimation. And remember that the Kramer-Rao lower bound theorem has also a second part which states that an efficient estimator exists if this equation holds. This the term here, the expression here, will be that efficient estimator, right? Just by substituting here the gradient of the log likelihood function that we computed in the previous slide, and here the Fischer information matrix that we obtained here, we come up with this equation, all right? And now by canceling terms, we obtain this one over here, right? So since this matrix H transpose H is invertible, right, we can multiply both sides by this its inverse, right, and therefore we find that theta hat x is obtained in this way, right? So since this expression is I mean, a perfectly valid estimator, it doesn't depend on unknown parameters, we can safely conclude that this is the efficient estimator. And remember that an efficient estimator is always MVU, and therefore we found our the sought MVU estimator for the Gaussian linear model. Okay. It is remarkable here that whenever you can formulate a problem using the Gaussian linear model, then you can just come here and use this expression as your estimator. You don't need to do all this math, right? So no need to apply the Cramer-Rao lower bound theorem if your problem is just a linear Gaussian model. This is a well-known expression, so call it a formula if you wish. Okay, so this is to sum up the efficient estimator when the noise is white, and therefore it is also the MVU estimator. Okay, so obviously it is a linear estimator, and it doesn't need knowledge of sigma square, right? So even if we don't know sigma square, we can still apply this estimator. That is an important benefit in practice, right? And regarding performance, we know that it is unbiased, and we know that its covariance equals the inverse of the Fischer information matrix, just because of the fact that it is efficient. But as a sanity check, let us compute it manually. So the expectation of this theta hat is, of course, this estimation of this term here, and by using the linearity of the expectation, we see that the expectation comes here. So we need to substitute the mean of x, which remember is h theta, right? And therefore this term here cancels with this term, and we obtain theta, right? So the estimator is, as expected, unbiased. And the covariance matrix can also be obtained just by using probability theory facts, right? Remember that the covariance of a matrix times a vector is just the matrix times the covariance of the vector times the transpose of the matrix, right? So we reviewed this in the review lecture on probability theory. And just by using the fact that this covariance is sigma square I, we find this, which is precisely the inverse of the Fischer information matrix, as we expected. Okay, so everything is looks good so far. Now, how do we obtain the an estimator or the MVU estimator in the case of colored noise? So you can do the same the derivation that we have done for white noise for using generic positive definite covariance matrix sigma, right? The same steps have to be done, right? The math is a little bit more tedious, but it is doable. Actually, you can try to practice, right? But in this case, we can use a trick that is called Prewhitening, which is commonly used in communications and in speech signal processing, image signal processing, in many areas. The trick is to multiply our data by the inverse of the square root of the covariance matrix, right? So since this matrix is assumed known, right, this operation can be done, right? And let's see why this operation is effective. So just by substituting the equation of our model, we obtain that this is our transformed data x prime, right? And here we can just define h prime to be the product of these two matrices, and w prime to be this transformed version of the noise, right? So this is again has the form of a Gaussian linear model, right? So since this W is Gaussian, then multiplying it by a matrix gives us also a Gaussian vector, right? So this is a fully qualified linear model, but now these matrices and this noise vector are different from the one that we had before, right? So note by the same property that we applied here, that the covariance of the noise, right, will be sigma minus 1/2 times the covariance of W, which is sigma, right, times sigma to the minus 1/2, right? And if we multiply these three matrices, we get the identity matrix, right? And therefore, this transformed noise W prime is has this distribution here, right? And now we see that it is actually white, right? The covariance matrix is a scaled identity. In particular, it is the identity matrix, right? So this is why we call this x prime the pre-whitened data, right? And this is a trick that we can always apply whenever we know the covariance matrix. So since we know how to obtain the MVU for the case where the noise is white, right, we can just apply this expression, right, here on this transformed model, right? And the estimator for theta will therefore become this one here, right? So we have just replaced this h with h prime, and this x and the x here with x prime. Okay. So now by just substituting back the values of h prime, right, we obtain this expression here, right? So this is our MVU estimator for the case where the noise is not white, right? So as you see, the trick is very smart, right? So the performance is again can be computed just by what we know. It is of course unbiased, right, because of this, right? And the covariance is can be obtained just by this expression here. We just need to replace this h with h prime, right? And again, substituting back the value of h prime, right, by this here, we obtain this expression, right? So you see that it is it indeed generalizes this, right? This is something that we should always check, right? If we set sigma to be precisely sigma square I, right, we recover the expressions here, right? So this would be this inverse would be 1 over sigma square I, right? And that 1 over sigma square, since this inverse is here, right, will come out as sigma square, right, as here, right? And similarly, here we will see that the 1 over sigma square here will cancel with the 1 over sigma square here. Okay. Okay, so let's just recap the main messages of today's lecture. We said that the Gaussian linear model is widely used. We actually used some examples to illustrate why it is so relevant. One of the main benefits is the simplicity and the fact that we know now the expression for the MVU estimator, right? And another benefits is, as we said, the sort of the generality, right? It arises in many applications, either exactly or approximately, right? We introduced the notion of identifiability, right? We said that a parameter is not identifiable if the distribution of the data is the same for different values of that parameter. This is a concept that applies in general in estimation theory, but we presented it today because in the context of the Gaussian linear model, it is easy to understand. And in this specific case, it imposes, identifiability imposes that the columns of the observation matrix must be linearly independent. We found the MVU estimator. In fact, this is the efficient estimator, right? It attains the Kramer-Rao lower bound, and we did so both for when the noise is white and when the noise is colored. So it remains to answer some open questions at this point. What happens if the model is nonlinear and we are not willing to approximate it using a Gaussian linear model? Perhaps that is a very poor approximation, right? What happens if the noise is not Gaussian, right? So another assumption here was that the noise is Gaussian, but this need not be the case in practice, right? And also, what if there are no efficient estimators, right? So the method that we have now to obtain MVU estimators is by relying on the Kramer-Rao lower bound theorem, and it may happen that we are not successful in applying it. So we will not answer these questions today. As always, we leave the suspense, and so thanks for your attention, and I'll see you in the next lecture.